All right. Hello, viewers, and today we're going to be solving some Diophantine equations using factorization over extensions of the integers. So the first equation we're going to be looking at is y squared equals x cubed minus 1. So on first glance, this equation is like, first of all, it's an elliptic curve, right? But it's also a Mordell curve. And we always know those have finitely many solutions, and there are techniques to find them. But here we're going to be going with some, uh, in some sense, simpler techniques, but still some very, very cool uh, stuff. So this is stuff that you don't see very often. Well, okay. So first of all, we look at this equation, and um, well, the first things first, you're not going to be able to solve this by taking some modulus, obviously, because we already have the solution 1 comma 0. No matter how many times you mod, you're not going to get any good information. And then you're not going to solve this like with some descent method either, because you see this is an elliptic curve, and basically descent methods get really complicated. So how do we solve this, right? That's a good question. So what we want to do first is we see this y squared and we see this 1, right? Let's move them onto the same side. Get something like x cubed equals y squared plus 1. And now if we could, these are two different squares, right? If this was a difference of squares, we could factor the difference of squares and then look at the possible GCDs, and then we could solve it based on the prime factors of x. But here we can't do that because this is not a difference of squares. This is a sum of squares, and you've been told all your life that you cannot factor sum of squares. But it turns out that's actually false. So what we're going to do is, instead of working in the integers c, we're going to extend the integers with I. And now you might think, okay, well, isn't this just like, I don't know, the complex numbers? Well, this is not true, because even though we extended it with I, that doesn't mean we automatically gain all the complex numbers. In fact, we only gain I, and like this is a ring. This is not we're not talking about a field here. Basically what happens is, not only do we have the integers 0, 1, 2, now we can go into imaginary numbers as well, but only in units. So we can have 1 plus I, maybe 2 plus I here. I mean, sorry, 1 plus 2I. We still have all the integers, but now we also have um, complex numbers where both coefficients are integers. Like this one is 3I. So we'll have all numbers of the form a plus bi, where a and b are integers. Now, this ring is called the Gaussian integers. Now, we don't need to worry too much about the complex theory behind like rings and whatever that make this possible. But don't worry, it's all sound, because the key is that we're given one very important fact, which is that for z extended, um, the fact is, when we extend z by certain square roots, like for example, square root of -1, or square root of um, like 3, and that sort of stuff. When we extend by certain numbers, this will become what is called a unique factorization domain, which means we have primes and all that. We have every number has a unique factorization, etc. All of those cool tools that seem like they would only apply to the integers, right? But it turns out there are a few other rings where this applies. This includes just a few negative numbers that can be square rooted, well, at least this type of thing, square root of some number. And there's a bunch of positive numbers you could square root, possibly infinite, but we don't know for sure. So let's proceed with the proof. So the key idea is that we can actually take this y squared plus 1 and factor it into something like y plus I times y minus I. Now, why does this work? so this is a difference of squares, right? It's going to be y minus I squared, but I squared is -1, so it's just y squared plus 1. So we can factor this into this. And let's look at, because if each of these were a cube, then there's a lot of easier ways we can approach this question. But for now, let's see what happens if there's something that divides them both. In other words, they have their greatest common denominator isn't 1. So let's say there's something that divides them both, right? Let's say this is A times that whatever thing that divides them both, and this is B times whatever thing that divides them both. Then it follows that their difference, which is A minus B times P, is also a multiple of whatever this thing that divides them both is, right? Now their difference is 2i. So that means whatever divides them both has to divide 2i. Now, what does that mean, right? Now, here's something important to note when we're working in this ring of Gaussian integers. And it's that there's a certain property of numbers called the norm of, let's say, a plus bi, that it's sort of like a determinant in some sense. So if you have the norm of a plus bi, and then you take a plus bi times c plus di, then the norm of the resulting number will be the same as the product of the norms of a plus bi and the norm of c plus di. So in some sense, it's sort of like a certain integer that is very, very intrinsically connected to these numbers. And it's basically just equal to a squared plus b squared. And you might say, okay, well, that's just the magnitude, right? And you'd be right. This is just the magnitude of the number. Since these are complex numbers, the product of two complex numbers has a magnitude equal to the product of the magnitudes of each of them. So this holds. Now we look at these norms, but this norm is a bit different in other ones. So like z of square root -3, the norm there will be slightly different, and we'll be looking into this soon. But first, let's look at this norm, right? So first of all, 2i is equal to 1 plus I squared. And this is not hard to see. We can just expand this, right? So it's nothing difficult. But then I claim that 1 plus I has to be a prime, at least in the extended with I. So why is this true? Well, the norm of 1 plus I is equal to 2, right? That means if it's the product of two things, then each of those norms has to be 1 or 2, because norms have to be integers. But if your norm is 1 in zi, you can only be +1, -1, I, or negative I. Now, the issue with this is all these numbers are what we call units. And basically, units, like in normal numbers, you know how we say, like, oh, you're only a prime if you're divisible by 1. And I mean, in integers, we say you're a prime if your only possible factorization is like 1 times yourself, right? Well, in Gaussian integers, it's slightly different because there's so many values that can have norm 1. So we say a number is a prime if the only possible factorizations have to have itself and 1, -1 I, or negative I. And in general, this is not true, but since this is a unique factorization domain, this is basically a close enough definition as far as we need. So we have 1 plus I as a prime because, like, there's no way you could factor 2 into something that isn't 2 and not have a 1. So basically, we can rewrite this 2i as 1 plus I squared. And that doesn't leave us with many options for our prime that divides both numbers. The prime has to be 1 plus I, basically. So now let's look at what happens if the prime is 1 plus I. So let's get rid of this. So if 1 plus I divides y plus I and it divides y minus I, well, something interesting is going on here. Because first of all, one thing you might notice is how many times 1 plus I divides y plus I. Well, we'll leave that up for now. But the point is, I and negative I are basically identical. And this is some like Galois theory magic. some black magic here. But if we swapped one, if you swapped I and negative I, then there isn't really too much difference because once you square these terms, they're going to become -1 anyways, right? There isn't much difference in the interaction. So it turns out v of 1 plus I of y plus I has to equal v of 1 minus I of y minus I because like negative I and I are basically identical, quote unquote, basically identical if we treat them like independently. So these two values have to be equal. And the interesting thing is, well, what is 1 plus I? What happens if, say, we took this and multiplied it by I? 1 minus I times I is I minus I squared, right? That's just 1 plus I. So what that means is these two primes are actually the same prime because, well, they're the same up to some unit factor, which is I. So it turns out we can get rid of this. This is not 1 minus I anymore. This is actually equal to v of 1 plus I of y minus I. And this is where things start getting interesting because here on the left side, we have a cube, right? So the v 1 plus I, uh, 1 plus I okay, never mind. The v 1 plus I of this x cubed has to be a multiple of 3. And this value has to equal this one, which means, well, obviously they can't both be 1, right? Because if they're both 1, then this is going to be 2. And, well, that just means you don't have 3 or you don't have 3. So that's obviously impossible. That means each of these has to have at least greater than or equal to 2 uh, factors of 1 plus I. But what happens after that? Well, remember how 1 plus I squared is basically 2 up to some unit? Well, it's 2I, but up to some unit, it's equal to 2. What that means that let's say we had something like a plus bi. After we multiply by 2, so this is basically saying any multiple of 2, it'll turn out to be like 2a plus 2bi, right? And that means both the real part and the imaginary part have to be even integers. Now, why is that so bad, you might ask? Well, there's a very good reason why this is so bad. And it's right here. Because the coefficient of I here is 1. And why is that bad? Well, 1 is not an even integer, is it? Right? 1 is not an even integer. So that means this is impossible. And that means there are no solutions if 1 plus I divides both of these numbers. So now we can just get rid of this case because, well, this case we just showed was impossible. But now we're very fortunate because this is exactly what we want to go for. And I'll show you very soon why this makes the equation so much simpler. So obviously now we know they don't share any prime factors at all, which means if this was some like, I don't know, p1 to the 6, p2 cubed, etc., then each of these prime factors either all has to go into one or all has to go into the other. And what that means is each of these values has to be a perfect cube themselves. And there's no way around that because you can't split these multiples of 3 up. They have to all be in one or they have to be all be in the other. And that means both of these have to be perfect cubes. And that makes our life 20 times easier. Why is that? Because now we can totally just like solve a simple equation. So let's say y plus I is c plus di cubed. Well, now we can just expand the left-hand side. We get like something like c cubed minus, I don't know, 3cd squared. But this is the real part. We don't really care about this. This is just going to be what y is equal to. We don't know anything about y, so we don't really care about this side of the equation. What we do care about is this other side of the equation, 3c squared d minus d cubed I. So this is the entire left-hand side, and this is going to equal y plus I. But now this is the story for this imaginary part is a bit different because we know that the imaginary part has to equal exactly 1. So this equals exactly 1. And now we have something else, another cubic. Now you might say, okay, well, we turn a cubic into a cubic. What's so easy about this one, right? But you got to pay attention, guys. You got to pay attention. This left-hand side is a multiple of d, and it equals 1. And you might recall, since we're working on Gaussian integers, c and d are both integers. What does that mean? Well, that means d has to divide 1. And, well, we're no longer working with a cubic here, are we? So if d divides 1, it has to either be 1 or negative 1. So if d is negative 1, we have something like negative c squared equals 0. That gives c equals 0. And if d is equal to if d is equal to positive 1, we have 3c squared minus 1 is equal to 1, so 3c squared is equal to 2. But the problem with that is, well, 3c squared is a multiple of 3, and 2 is not a multiple of 3, so there's no solution in that case. That means d has to equal negative 1, c has to equal 1. So we only have one solution, which is 0 minus I. Cubed equals y plus I. Now, what is negative I cubed? Well, negative I cubed is just equal to positive I. So that means if this side is equal to positive I and this is the only solution, that means y has to equal 0. If y equals 0, well, the only possible solutions have to have y equals 0. And now we can plug back to the original equation. When y equals 0, we have x cubed equals 1. So we get that our only solution, which works, is 1 comma 0. And we've solved this equation. Now you might say, okay, well, so what? This is like so trivial. Why do we even need to go through this? Well, it looks trivial, but when we start applying these to some more complicated equations, our method will still work, but then we'll start to make actual interesting progress. So just to demonstrate, let's just move on to our next example. So we're going to change something about this equation, make it slightly more interesting, not too much more interesting, because we'll get to the actually juicy one later on. But you'll notice all the questions here are going to be pretty similar. So let's move on to the next one. The next one will be y squared equals x cubed and minus 1. Wait, this is the same question, right? Oops. So we're going to change this very, very slightly to make it a more interesting question. We're going to make this 1 into a 2. Now we have y squared equals x cubed minus 2. How do we solve this? Well, first of all, the first step is not to go about screaming that this is a trivial again, because now this is not trivial anymore. The solution we have in mind, the reason modulo doesn't work, obviously, is 3 comma 5. And you might still say this is pretty trivial. I do not disagree, but I mean, there's no zeros and ones. I think that counts for something at least. So 27 minus 2 is equal to 25. But now how do we go about solving this equation? Well, we can do something similar. X cubed equals y squared plus 2. But now you're here and you're like, oh no, we still can't factorize this. Because last time we did plus 1, right? We could factor into like square root of negative 1. But how do we do this one? It's hard, right? This 2 isn't a 1. But how do we fix that? Well, we don't need to fix that part. What we can fix instead is the field the ring that we're working over. So we were working over z extended by square root of negative 1. But now what we can do is we can work over a slightly different ring to make it possible again. But don't take this for granted, of course, because there are not many rings where we can do this factorization successfully. So in particular, there's only finitely many negative, like square root of a negative number that work, where the negative number is an integer. But for now, just keep in mind, we can do square root of negative 2. This is possible. We can also do a few other negative ones, like negative 3, negative 7, negative 11, negative 19. But don't take these for granted. There's only finitely many. There's just like 2 or 3 more you could do over, but these are very special because you get to do unique factorization over these rings. So let's proceed with our ring z extended by square root of -2. So what happens now, right? This is equal to, and yes, this is one of the unique factorizations domains. So here on the left side, it's y plus root -2 times y minus root -2 for the same reason as before. And we can do the same idea. So something that divides both sides has to divide, well, their difference, right? And the difference is just 2 root -2. So let's say whatever divides both to divide this. But turns out 2 root -2 is just negative of root -2 cubed. And this shouldn't be too hard to see. Well, you just expand it, right? This is a unit, so we ignore that. So basically, p has to divide square root of -2 cubed. Now, well, what does that mean? Square root of -2 turns out to be a prime. Now, why is that the case? Well, we can do a similar norm here, like we did before. The norm is just going to be a squared plus 2bi. I mean, sorry, 2b squared, where elements in here are a plus b root -2. And this norm works for like the exact same reason as the last one. It's just now we have this 2 here because this square root -2 term is, well, the magnitude is different, right? And this works for a similar reason as this is just like a magnitude, right? Magnitude squared. So this is multiplicative. Um, but the point is the norm of root -2 is just 2, right? And 2, you're not going to factor that into anything magical when you're only working with integers. So that means this root -2 is a prime. So in order for p to divide this square root negative, and by the way, keep in mind, this is not a unit. Even though this is like 0, comma 1, it's trivial looking. It doesn't have any real big numbers. This is not a unit. For it to be a unit, you have to have some value times it that equals the multiplicative identity. But that's impossible because you want 2 times some integer to equal 1. Good luck doing that. 1's not even. So that's not going to work out too well for you. So this is not a unit, which is why it can be a prime. Anyways, let's proceed. So that means if p is a prime that divides both of them, it has to be square root of -2. So let's proceed. If square root of -2 divides both sides, then for a similar reason as before, because like some Galois theory magic or something, there's probably a simpler explanation. But that means VP of this side equals VP of this side, and it has to be a multiple of 3. Well, what does that mean? That means VP of both of these has to be greater than or equal to 2. And I think we all know the issue with that. If -2 squared divides this value, let's y plus square root of -2. Well, what is -2 squared? That's just -2, right? Up to a unit, that's just equal to 2. That means the coefficient of square root of -2 has to be an even number. But the coefficient here is 1. And again, for the third time, 1 is not an even number, so this is not going to work out. That means these two numbers do not share any prime factors. So that makes our life a lot easier because now we can solve the equation. So now we can just say c plus d root -2 cubed is equal to y plus root -2. And now that we are aware that we only really care about this imaginary-esque part, we'll just take out the parts that actually matter. So that's just going to be 3c squared d minus 4d cubed times root -2. And this is going to equal positive 1. So what do we do now? Well, oh, sorry. This is the extra part that corresponds to this root -2. So this part equals 1. Now, once again, we see that this left side is a multiple of d. D is an integer, so d divides 1. So d has to be plus or minus 1. Now we can look at the two cases. If d is equal to 1, we have 3c squared minus 4 is equal to 1. So 3c squared equals 5. 5 is not a multiple of 3, so that's not going to work out for you. Then we look at the other case, d equals equal to negative 1. So we get negative 3c squared plus 4 equals 1. So move this to the other side. We get c squared equals 1. So c has to equal plus or minus 1. So our solutions are going to be 1 minus 1 minus square root negative 2 and negative 1 minus square root negative 2. Now, what do these values turn out to be? Well, it's not really too hard to extract now that we have the answers, right? If these are the only values for this thing on the left-hand side, we just cube them and we can get y plus root negative 2. So what is the cube of this? Cube of this is just 1 minus 3 root negative 2 minus 6 plus 4 root negative 2. This is going to give negative 5 plus root negative 2. And I will point out this side is basically identical to this. This is going to be some negative version of this. It's going to be like, well, the resulting number is going to be 5 plus root negative 2 when you cube it. What does that tell us? That tells us y is equal to 5. It's the only possible solution. So what happens when y equals 5? Well, we just get this solution. This is going to be only 1. So the only solutions have to have y equals 5. And when y equals 5, this is the only solution, which works. So that means we get, here is our answer, 3 comma negative 5. Pretty nice, right? Pretty nice. So now let's move on to something even less trivial. And the trivial notist of all of these. Okay, that is not a word. But finally, let's move on to our final example, which will seem oh so close to all of these ones before, but there will be something very different about it. It's going to be slightly less trivial. The first one, this was the only solution. Second one, this is the only solution. Now let's see something that doesn't have just one solution, right? Something that has two solutions. We're not going to go too far off. Our next example is going to be y squared equals x cubed minus, what is the magic number? Okay, we started with 1, then we went to 2. So that means this number must be 4. Of course. So let's look at this equation. What solutions are obvious? Obvious solutions are just 2 comma 2. And we're just going to ignore negative solutions because they're basically identical. The obvious solution is 2 comma 2 because 8 minus 4 is 4. And the slightly less obvious solution will be 5 comma 11 because 125 minus 4 is 121, which is 11 squared. So, there are 2 solutions. Now, this is getting a bit intimidating. Does that mean our method's going to fail? Like 2 solutions, we have never seen this before? Of course not. You got to trust in the method, right? So let's continue. So how do we do this? Well, first let's put this in the form we want. X cubed is equal to y squared plus 4. Now, you don't want to be naive here. You might see this plus 4 and be like, oh no, there's no square root of negative 4 extension, right? Well, might you notice this is just 2 negative 1. So this is nothing new. Really, we can just use our square root negative 1 extension to solve this question. So let's use I again. Go back to our trusty z extended with I, the Gaussian integers. This is going to be y plus 2i times y minus 2i. Now, we're going to come back to this, and we're going to see, for the same reason, a number that divides both of these values has to divide 4i, right? So it has to divide 4 up to some unit. And once again, our trusty friend 4 is just going to be basically equal to 1 plus I to the 4th up to some unit. So with the same logic, we have v of 1 plus I is the same of this as this. That means since this is a cube, both of these have to have greater than or equal to 2. That means both of them have to be multiples of 2. But now here is where we meet our first issue. Because, well, well, you might ask, why can't we just do the same thing as before? It's still even. Well, you got to pay attention, guys. You got to pay attention. This is a 2. Our previous contradiction was that, well, this can't be an even number because it's 1, but it's 2. And it turns out, for some odd reason, 2 is an even number, right? That's so weird. So that means we can't apply the same approach of contradiction to this equation, but we can do something slightly different, which is noticing that since this is a multiple of 2, y has to be even. Let's say y is equal to 2k. And finally, we have to take a moment to stop using our machinery and start looking at what's actually happening. We get x cubed is equal to 4k squared plus 4. So that means x has to be even, obviously, because x cubed is even. So let's say x is equal to, I don't know, 2m. And these are bad choices of variables here. Then the left-hand side becomes 8m cubed. So if we divide both sides by 4, we get 2m cubed is equal to k squared plus 1. Now, how do we solve this equation, right? It seems like we're going on some kind of like an adventure trying to solve this question. But it won't be too hard. It won't be too hard. Why is that? Well, another equation, that's just another place to apply our method, right? Now we can factor this again. We get 2m cubed is equal to what? It's equal to k plus I times k minus I. Now, the only thing that could divide both these numbers, we're just going to take a previous result. The only value that could divide both these numbers is 1 plus I, right? Or 1 minus I, but that's identical. But if 1 plus I divides both these numbers, the issue is we have a 2 on this side here, right? That means 1 plus I has to divide at least one of them. And if it divides one, has to divide the other. So we're going to be looking, if both of them divide one of them, we're going to get a contradiction. Because if 1 plus I squared divides this one, then there has to be even. 1 is not even, so that's not going to work out. So there has to be exactly a 1 plus I dividing this side and a 1 plus I dividing this side. But now what the issue is that m cubed now equals these two values. And there's no more prime factors to divide both, because otherwise we're going to get the even contradiction again. So that means k plus I has to equal 1 plus I times some magic cube, c plus di. Cubed. Now this is not too hard. It's slightly harder because you need to do one extra multiplication, but I hope you are all able to deal with one extra multiplication. Hope you guys don't mind. This would be c cubed plus 2c squared d I minus 3cd squared minus d cubed. And then we multiply by 1 plus I. Now, what does this equal? Well, if we multiply by 1 plus I, we're going to get c cubed. Okay, well, we don't care about the real part. We really just care about this imaginary part. So we're just going to look at that part. If we multiply by 1 plus I, we just need to care about the I times the real part and the 1 times the imaginary part. That's basically just going to be addition. So c cubed plus 3c squared d minus 3cd squared minus d cubed equals 1. But sadly, although we try to be clever, there is, well, c doesn't divide all these terms, right? And d doesn't divide all these terms. So how do we proceed? Now, this is a good question, but it's not too hard to answer. So let's erase the board for now. Let's get the equation back on the board. C cubed. Oh, and sorry. This should be minus, no, sorry. Plus 3c squared d minus 3cd squared minus d cubed equals 1. How do we solve this? Well, it turns out c minus d divides this side. This is c minus d times c squared plus 4cd plus d squared. And this is just factorization, right? It's nothing hard to do. So this equals 1. So c minus d has to be plus or minus 1. And lucky for us, that gives only very few solutions. So let's look at the first one. C equals d plus 1. What does this expand into? Now, this is kind of annoying, but we can just look at this part. This is going to be d 60 squared plus 60 plus some like 1 equals 1. So now we have 6 times d squared plus 6d equals 0. That's not too hard to do. We can just factor 6d times d plus 1 equals 0. So d has to equal 0 or 1. I mean, sorry, 0 or negative 1. This doesn't give us too many tuples to work with. This has 1 comma 0 and 0 comma negative 1. Now you might ask, what if d is 1 more than c? Now I would say that is a good question, but the point is it isn't too hard to do. So if d is 1 more than c, then d minus 1 is just c, right? And this isn't too hard to process. This will just give d is equal to 0 or 1. For a similar reason, really we can just factor. What ends up happening is like 60 squared minus 60 plus 1 equals 1. So for the same reason, if d is 1 less than c, then our solutions are, if d is 1 more than c, our solutions are going to be negative 1 comma 0, or and our other solution is going to be 0 comma 1. All pretty trivial looking, right? So what does this mean, really? This means the only solutions to this equation that we have result from these values. So we're going to have 1 cubed, which is just 1. So, okay, and we have to remember to multiply these by 1 plus I. So we have 1 times 1 plus I. That'll give us 1 plus I. We have this cube times 1 plus I. That'll give us negative 1 minus I, but minus I is not what we're looking for. We're looking for positive I because it's going to be some integer plus just I. So this is not 1. This one here represents I, but I cubed is negative I times 1 plus I. That's going to give us like 1 minus I. That's not what we're looking for. We need to end with something that's plus I. And then finally, we have this one. This is going to be negative I. So negative I cubed, it gives us positive I. Times 1 plus I gives us negative 1 plus I, which is the other solution we're looking for, negative 1 plus I. So what this tells us is the only solutions have to have y equals 1 or negative 1. what does that mean? Well, we can just plug back into the original equation. And in case all of you forgot, the sub-equation we're trying to solve right now is 2m cubed equals k squared plus 1. And somewhere along the line, our k's turned to y's. I'm not sure where, but either way, k has to equal plus or minus 1. And that means the right-hand side is equal to 2, so m has to equal 1. Our only solutions are 1, comma 1, and 1, comma negative 1. Now, what do these solutions correspond to? Well, don't forget, m and k are just half of x and y. So that means these translate to 2, comma 2, and 2, comma negative 2, respectively. And there we go. Our first trivial solutions, well, trivial-ish solutions have been found. Now we just need to solve the other case to find our final solutions. So now let's get out of this world and return back to the equation we're actually trying to solve, which is y squared is equal to, y cubed is equal to x plus 2i times x minus 2i. And now we know, since like we already looked at the case where 1 plus I divides both these numbers, and turns out we get these solutions. So now we just need to look at the case where, well, these two numbers are just not, they don't share any prime factors, which means they both have to be perfect cubes. So x plus 2i equals c plus di cubed. Now, what does this mean? Well, again, we can just look at the imaginary part. We can expand this as 3c squared d minus d cubed I plus some other part. This is going to give us that 3c squared d minus d cubed is equal to 2. Now, our life is still not easy because this is not a 1, but we still have the d divides 2. So there are many cases here. D is either plus or minus 1, or it has to be plus or minus 2. It's not too hard to just check all of them. So let's look at all of them. If d is equal to, let's say, 2, then we have 6c squared minus 8 is equal to 2. So what do we get from that? We get 6c squared is equal to 10. Sadly, 10 is not a multiple of 6, so 2 is not going to be a friendly solution. Let's just write these out. So we have that 2 is not possible. Take a big X. What about 1? 3c squared minus 1 is equal to 2. 3c squared equals 3. So 1 does have solutions. C is equal to plus or minus 1. What about negative 1? Negative 3c squared is plus 1 equals 2. So negative 3c squared is equal to 1. Sadly, 1 is not a multiple of negative 3, so this is not going to be possible. Finally, we look at negative 2. What is negative 2? Well, negative 6c squared plus 8 is equal to 2. So we're going to get negative 6c squared is equal to negative 6. So c is equal to plus or minus 1. So this has solutions too, which basically look the same. It's not looking good for us, is it? Because we have two trivial solutions. These are like plus or minus 1s and negative 2s. Where in the world are we ever going to get that 511 solution, right? Turns out it's actually not too surprising where that 511 solution comes from. So let's return. Because even though we have all our solutions here, this is concealing something. C and I can still be cubed, which means the actual values of the numbers can be a lot bigger. So first we have 1 plus I cubed. What does this give us? Well, 1 plus I cubed, it's not too hard to find. This is just going to equal, like, it's some unit times 2. Wait, okay. We can't do units here. So this is going to equal 2i times 1 plus I. That's just going to be negative 2 plus 2i. So y equals negative 2 there. And this is nothing surprising, really, because, well, the truth is we have this already. Oops. So this is nothing new. Let's continue on. What if y minus I? Oh, sorry. This c is plus or minus 1. Negative 1 plus I cubed. Well, this is nothing surprising either. This is just going to give us negative 1 plus 3. That's just going to be 2 plus 2i. And this is nothing surprising. This is just going to give us the solution we had before. But now we get to the juicy solutions. This is an example of a juicy solution. So negative 2, 1 plus negative 2i cubed. What does this equal? Well, we can just expand, right? And really, we don't really care about the imaginary part. What we can do is to check our work anyways. So 1 minus 6i minus 12. And then, I don't know, like plus 8 or something. Plus 8i. This is going to give us negative 11 comma 2i. I mean, plus 2i. And the other one is negative 1 minus 2i cubed. And this is not too hard to find either. This gets negative. This gets negative. This is just going to be 11 plus 2i. So there we go. Now we have 11 finally appearing, right? The solution is starting to reveal itself. So this means I forget our variables in the original equation. It was probably something like y squared equals, y cubed equals x squared plus 4. Wait, was it though? No. It was something, okay. It was probably actually x cubed equals y squared plus 4. So now that we know that y is plus or minus 11, we plug that in and we get that 5, 11, and 5, negative 11 are indeed solutions. And that ends our journey of solving this question. With the magic of these integer extensions, we have solved these difficult looking questions and found all of their solutions. 2 comma 2, 2 comma negative 2, and 5 comma 11, 5 comma negative 11. And there we go. So all in all, I thought this was a pretty clever technique that I've learned from some pretty strong people in math. Hope you find uses for these, and see you next time.